I'm Alex.
Hi, I'm John, and this is the fourth episode of Ask the Physics Majors.
We're physics majors, in case you're wondering.
Otherwise, we would have called the show this.
Oh, we might have. Our question today, from Words and Sturf, is how fast does Thor need to swing Mjolnir in order to gain liftoff?
This is a great momentum question. Momentum is the mass of object times its velocity. Now, we're going to be dealing with a system of objects, Thor and his hammer. We're going to pretend there's no outside forces affecting the two, which means that the system of Thor and his hammer will be independent from the outside universe, and the momentum initial of the system of the two objects' momentum added together will equal the final momentum of the system where his hammer and himself are joined and moving upwards.
All right, time for the equations.
What's happening in this problem? We have Thor, and Thor is spinning his hammer, like a Thor does. And as he's spinning it, it's going to be having constant speed. And when he lets go of his hammer, it will continue going with the same speed in the direction it's moving when he lets go. If he lets go as it's going up, it will move up. And as he lets go, he now grabs onto his hammer. As he grabs the hammer, the system of him and his hammer will have to conserve their momentum. That means his hammer's velocity will slow down and his velocity will speed up so they're the same as they move. And then they're going to move together upward, and we hope to get them to reach a height of 30 meters. We call this an inelastic collision. It's when two objects that won't connected and moving together, Thor at the ground, and then him grabbing his hammer after he releases it, are now connected together and move together upwards or to a direction, but they're now acting as one body with one velocity. Now, Alex will show you the math.
I'm back with the math, and he gets the roller chair while I don't. Looking at this problem, as John said, we're going to imagine Thor goes up to a height of 30 meters. For the purposes of our argument, we're going to assume that he just goes straight up and comes back down. If he was going horizontally, it's due to wind for the purposes of our calculations. Now, at the top of the parabola, he has a speed of 0 meters per second. First things first is we need to figure out how fast the system, both Thor and his hammer, need to leave the ground. In order to find his velocity he needs to leave the ground, we're going to use something called the conservation of energy, which states that, oh, hi, John. Welcome back to the math portion of our video. Bye, John. Conservation of energy. That's where I left off. That states that energy initial equals energy final. So for us, that would mean the energy that both Thor and the hammer has on the ground would be the same as the energy he has up here at 30 meters. Now, moving over to my math, e.g., gravitational energy, is equal to the mass of the system, or mass 1, which we've labeled here as mh plus mt, where mh stands for the mass of Thor's hammer, plus the mass of Thor himself, times the acceleration due to gravity, times the height that you are at. And kinetic energy is equal to 1/2 mass of the system times velocity of the system squared. Doing our calculations, we would set it up as m1 times g times h is equal to 1/2 m velocity of the system squared. That would actually be m1. Looking at this, we can see that there's an m on both sides, so we can divide everything by m1 to cancel it, leaving us with gh is equal to 1/2 velocity of the system squared. I apologize for my handwriting, sometimes it gets kind of bad. Our acceleration due to gravity is equal to 10 meters per second squared. So we can put that in as 10, and then our height is 30 meters, so we'll put in a 30 here, and then that's equal to 1/2 our velocity of the system, which we're solving for, so we'll just leave that as vs squared. Now, doing some fancy math, we get the answer to be vs is equal to 10 root 6, or approximately 24 meters per second. The velocity of the system here is 24 meters per second. That's how fast both Thor and his hammer need to leave the ground. However, the question is not how fast does Thor and his hammer need to be, it's how fast does the hammer need to be. We're going to use another set of equations and another principle called the conservation of momentum, which is right here. Conservation of momentum in an inelastic collision can be written as the momentum of object 1 plus momentum of object 2 equals their final momentum. Splitting that up, we have the mass of the hammer times velocity of the hammer, or object 1, plus mass of Thor plus velocity of, times velocity of Thor is equal to their combined masses times the velocity of the system. Now we just found out from our conservation of energy that Vs is equal to 24 meters per second. So we can plug that in. And we also have the mass of the hammer as 19.2 kilograms and the mass of Thor as 290 kilograms. Plugging in our known variables, we get 19.2 times velocity of the hammer plus the mass of Thor, which is 290 kilograms, plus times his velocity. Why do I keep saying addition? I don't know, but it's multiplication, guys. The velocity of Thor would be 0 when he grabs the hammer, because he's standing still at the instant that he grabs it. So we can just put a big fat 0 there. And that would be equal to their combined masses, which would be 309.2 times the velocity of the system, which we wrote here, which is 24. We find that the velocity should be 386.5 meters per second. For some reference, we're going to have to pause again while I do some other calculations. And we're back with velocity of Thor's hammer. The velocity that Mjolnir needs to be swung by Thor is 386.5 meters per second. Now for some perspective, converting that to miles per hour, we get 864.6.
That's fast.
Real fast. Cars have issues driving that fast. Cars need jet engines to go that fast.
That should whip his arm off.
Maybe. Anyway, this is how fast Mjolnir needs to be swung. I will underline it for some emphasis. And we're back. If you enjoyed this video with me and John, like and subscribe
To Heroic Science. And if you want to see us answer more fun physics questions, leave a comment below in this video and maybe your question will be the next question answered in Ask the Physics Majors.
Will it rip his arm off? I don't know. Tune in next week. Maybe that's a question you want to ask.